Okay. So kind of the last topic in section 1.5 is what the heat equation looks like in other coordinate systems. Okay. And so in this part, what we're going to do is we're going to focus on two systems in particular, polar coordinates, as well as spherical coordinates. Okay, and I'll review what these coordinate systems are, but then we'll talk through some of the computations to kind of re-express this operator nabla squared, right? That diffusion piece in the heat equation. What we want to do is express that with respect to different coordinate systems. Okay, and turns out it's not super, let's say, trivial. There are a few steps that we have to be careful about. Okay? It's not a matter of just replacing x, y, and z with rho, phi, and theta, for example. Okay. So what do I mean by all of that? So in 2D, right, this operator nabla squared u, right, this was nabla squared was divergence of the gradient. Okay. In 2 dimensions, it takes this form. Okay, to sum up the second derivatives with respect to each spatial variable. In 3D, it's almost the same. You just add that second derivative with respect to z. Okay. So what we want to do is figure out a similar expression for kind of a polar coordinate system. Okay, so what are polar coordinates? Let's review. If so zooming in for a second here, so if that dot is the point xy, right, and kind of in our Euclidean coordinate system, you know, so many units, x units to the right, y units up. Okay, we can either express it in terms of x and y, or we can express it in terms of, if we draw a vector connecting the origin to the point that we care about, what we can do is compute what the angle is between the vector kind of and the x-axis, as well as the radius or the length, say, of that vector. Okay. And so all the information that we get from x comma y, right, where we are in space with respect to x and y, all that information we also get from the pair r and theta. Okay. What's the conversion? Well, our x coordinate is going to be r times cosine of theta, right? Cosine of theta is the kind of, right, horizontal contribution of the vector. Y, which is going to be r times sine theta. This is the vertical component or the contribution of the vector from the origin to xy. Okay. So, okay, so those are polar coordinates. So what does this operator, right, nabla squared of u look like with respect to this coordinate system? Comes this. May or may not be a surprise, may or may not be expecting something nicer or simpler. But if instead of working with your function u in terms of x and y, instead if you want in terms of r and theta, then this is what you're computing whenever you compute this quantity. But the key thing is that this whole expression right here, this is equal to, right, d dx squared of u plus d dy squared of u. Okay. So that's in polar coordinates. Okay. We can also ask the same thing with spherical coordinates. Here, if you have a vector right there, that's going to be the point x, y, z. Okay. So x, y, z is the Euclidean coordinate system. What we can do is we can also specify that point using three different quantities. R, which is going to be the distance to the origin. Okay. And then we have these two angles, theta and phi, that give you a sort of spherical coordinate system. Okay. So for polar coordinates, right, implicit here is we had a circle and theta was telling us where along the circle we were. And then R was saying how far kind of out of the circle we had to go. Here, theta and phi are telling us where on the sphere we are. And then R is saying how far out or how far in within the sphere do we have to be. Okay. Generally, or at least the coordinate system we'll use, theta refers to this sort of rotation around. Okay, so like here, so where I'm facing right now, theta would be 0. As I start to turn, theta would be increasing until I get to all the way to 2 pi. Theta is 2 pi, or theta is 0 again. Okay, so it's theta. The other variable is phi. Okay, what is phi? Well, if you look straight up at the North Pole, that's phi is equal to 0. As you start looking down, phi is increasing until you're looking all the way at the South Pole. And at that point, phi is going to be pi. Okay. So maybe written out. So theta. So what values can these take? Theta is between 0 and 2 pi. Phi is between 0 and pi. Okay. It's just another coordinate system describing space. Okay. So this is a coordinate system. The question is, what is Navier squared? What does this diffusion piece, this operator look like? It looks like this. Okay. These are not things that you'll be expected to kind of remember off the top of your head. If we ever need to use these, they'll be provided. But it's just, if you change the coordinate system, your operator might change its appearance by a lot. Yeah, it'll change its appearance. Okay. So what we're going to do is we're going to try to, we are going to derive at least the expression for polar coordinates. Okay. And so to do that, what we're going to do is we're going to kind of work with this div grad formulation, right? Navier squared of u is this operator divergence times this operator grad of u. Okay, so our game plan is going to be express div and express grad in terms of polar coordinates, and then plug all of that in here, and then we'll end up with this expression. Okay. Yeah, so what are these in terms of, what are gradient divergence in terms of polar coordinates? Well, we can start to compute these using kind of the chain rule. Okay. And so what do I mean by that? Where are we going with this? Well, so U is our temperature. We want to know U in terms of the radius and kind of the angle in polar coordinates. But keep in mind that the radius, right, where your point is, we can express that in terms of Euclidean coordinates, right? So as you move X and you move Y, the radius is going to change, okay? So the radius is going to be a function of X and Y. Similarly, the angle is also going to be a function of X and Y. Yeah, okay. So we're treating our function like this, okay? It's a function of two functions. And what we're going to do is we're just going to take an x derivative. Okay. And this is where the chain rule, multivariate chain rule comes in. Okay. So how does u vary with x? Okay. Well, I can write it again here. So remember, u was a function of r and theta. Okay. And r and theta were functions of x and y. So if we want to know how u changes with respect to x, well, first we need to know how u changes with respect to its first argument, which is r. That's this derivative. Okay. And we also need to know how this first argument changes with respect to x. Okay. And that's the second piece. So that's how u varies with x, kind of with respect to the first argument of u, right? This r argument. And then we need to add in how u changes with respect to theta. Okay, but it's the same thing. How does u change with respect to its second argument? How does that second argument change with respect to x? Okay. And so what I did here, just here, so change the places of these two things, which may seem not much, but we'll see why it's important in a second, valuable in a second. So just switch the position of each of these terms. And then now what we're going to do is kind of factor out this u. Okay. So we're going to get an expression like this, right? So are these two the same? Well, you can compute. Here, we're applying this differential operator to this function. How do we compute that? Well, distribute u over the sum. Okay. In the first place here, this is just going to be some function, some scalar. This is going to be something that can actually act on u. So this acts on u. And then we get this thing up here. Okay. So it's just one way of rewriting this piece. Okay. So yeah, so we almost have everything. Question is, well, what is this? Can we actually write down what this partial derivative of this function is? Okay, and so that's kind of where we're going with this. So keep in mind, right, what is that length of the vector, right? What's the kind of value of r? Well, r squared is going to be x squared plus y squared. It's essentially Pythagorean theorem. Okay. But because r squared is x squared plus y squared, we can take the derivative of each side with respect to r. And so the left-hand side, right, or sorry, take the derivatives with respect to x. And again, this function r is still going to depend on x, okay? So on the left-hand side, this is the expression that we want to compute. Chain rule again, the 2 comes down. So you have the derivative of the outside times the derivative of the inside. Derivative of the outside is 2r. Okay. Derivative of the inside is the partial of r with respect to x. What else do we have? Well, on the right-hand side, take the derivative of that with respect to x. Y doesn't depend on x. We're treating these as independent coordinates. So the x derivative of the right-hand side is just going to be 2x. Putting all that together, we get the partial derivative of r with respect to x is x over r. But what is x in polar coordinates? That's r cosine theta. So r cosine theta over r is equal to cosine of theta. Okay. So all of this stuff here, right, this little derivation, that was to compute this piece, which shows up right here. Okay. So this derivative with respect to x, we know half of what it looks like. It's going to be cosine of theta times ddr. Okay. We also need to know what the coefficient is for this dd theta derivative. Okay. And so that's what we do. We can do next. So we can also write, so how does theta relate to x and y? Well, y over x, assuming x isn't 0. Y over x, that's the slope of your vector. Okay. What is that slope? It turns out to be tangent of the angle that tangent of theta is the slope of your vector. But here we can do the same thing. So what is the x derivative of tangent of theta? Chain rule here, derivative of the outside, right? Derivative of tangent theta is 1 over cosine squared of theta, times, so derivative of the outside times derivative of the inside, which theta is a function of x, so we get d theta dx. Okay. So that's half of it. The other half is, well, what is the x derivative of y over x? That's going to be minus y over x squared. Okay. So putting these together, what do we get? Well, 1 over cosine squared theta is times d theta dx is minus y over x squared. We know what y and x are in terms of polar coordinates, right? Y is our sine theta, x is our cosine theta. So we plugging those in, we get this expression. Okay, moving this this cosine squared up there, canceling, rearranging, doing whatever. We get our final expression. Here's how theta varies with respect to x. Okay, minus sine theta over r. Okay. So what do we get? So to summarize, these two pieces we just computed. Okay. These two pieces we can compute in almost exactly the same way. Okay. So why are these useful? Well, this gradient operator, okay. How does this work? Well, right, plug in gradient of u, you plug in a u right there, plug in a u right there, okay. But what we did, so way back up here, for example, was we said, well, d dx is equal to this thing. Okay, so now what we're going to do is we're going to plug in d dx, and in particular, plug in these coefficients here to express the gradient in terms of polar coordinates. Okay. So what do you get? Well, d dx, okay, from the derivation above takes this form. D dy, you get pretty much exact same thing, except you care about how r varies with respect to y and how theta varies with respect to y. Okay. But now what we're going to do is for each of these coefficients, we're going to plug in what was computed right here. And so if we plug in the coefficients, so dr dx, right, if we recall, dr dx was cosine theta. So we're plugging in the cosine theta for that, which is right there. And then we're also plugging in for this d theta dx, which is this minus sine theta r. Okay, so that's that first piece. Second piece is going to be this expression, which you can check. Okay? All of this so far is just computations. Right, so that's our gradient operator in terms of polar coordinates. Okay, and we got that via the chain rule. So what about divergence? Well, recall you have a vector field phi. It has two pieces, f1 and f2. The divergence of phi is going to be how f1 varies with respect to x, first component of the vector field, plus how the second component of the vector field varies with respect to y. Okay, well, what was, yeah, so what we're doing here, so what was d dx in terms of polar coordinates? So this expression where we haven't yet plugged in for dr dx and d theta dx. What about f2 or d dy of f2? That takes that form. Okay. And so if we plug in for these coefficients, we get, so this is equal to this, and then this is equal to this. And that's like, yeah, that's the divergence in terms of polar coordinates. Okay. Again, old computation. So now we're in a position to actually compute what this operator, right, divergence of the gradient of u, or nabla squared. This is nabla squared of u. Now we're in a position to compute what this is in terms of polar coordinates. Okay, so writing things out, we get this. Okay, and this you can check, which is computation. Do a bunch of steps, bring things together, terms will cancel, and in the end, you should end up with what was promised, which somehow miraculously is this. Okay, so homework: verify these ... Okay? But it is just a computation, and this is what the this operator, the square root of u, looks like when u is a function of r and theta. Okay? And then maybe time as well, if we're asking about temperature and time. But this thing right here only cares about the spatial piece. Okay? And that's what this operator looks like in polar coordinates.